You're listening to the Valley Current.
You've been doing this for a while. Of course, there's so many different domains that probability management, the nonprofit that you run and have been successful in trying to convince everyone that they should get on board, has found a new domain. And tell us more about what that is.
What this is really a pitch for is extending the gauge to really focus on climate change, climate risk, which we have not in the past, and it has some properties of its own that we need to address. At any rate, I want to thank all these folks for data. I also want to thank the Pew Charitable Trust for supporting an event on fire risk. It was kind of a private event, right? But that was very useful in getting a bunch of us together. And the problems are so big. No. The problems are so universal.
Mm-hmm.
And the fruit is so low hanging that when you get knowledgeable people together, good stuff happens.
Mm-hmm.
I give you the definition of risk that you will find all over the place. This is from the CIO website, whatever it is, CIO magazine or whatever. Okay.
Right.
Risk equals likelihood times impact. Okay, I got it. This means, let's take fire risk. So a fire with 1 chance in 10 of 1 fatality has an average risk of 0.1 fatalities.
Yeah, I should tell you, this is called in the law the learned hand formula, the P times L equation, where P is the probability or likelihood and the L is the expected liability or the actual liability that you're discounting for the risk. So this is used in negligence cases to say,
like for over 100 years or so, right?
Right.
And this goes back to way pre-computers,
yes.
by the way.
Yes.
Right? And this is the correct average risk. Okay.
Right.
But let's look at another case. How about a fire with 1 chance in 10 million of 1 million fatalities? Let's do the math.
Mm-hmm.
Likelihood times impact, an average risk of 0.1 fatalities? The same as this one?
Right.
To quote Lewis Black, are you shitting me? And is this embedded in our regulations? Yes. Okay, so we can do better. This is something that I call the flaw of averages. The flaw of averages actually is like an amalgam of several horrible mathematical mistakes. I got a house. It's worth $500,000. 1 chance in 100, it'll burn down. And you have to have a time period, right?
Right.
Annual risk. The risk is $5,000. If I had 100 identical houses, they're in town A, okay? They're all identical to that house. Right. Each one has 1 chance in 100 burning down every year. And all we have to do to get the average risk for the whole town is multiply 100 times the 5,000, and the average risk is truly $500,000, right? And that is true. It is the average. Okay. Now, to see how brain dead this is, that's town A. Let me introduce you to town B. Town B also has 100 houses. And each house has 1 chance in 100 of burning down every year. And each house has a $500,000 value. Well, that's it. Town B also has a total annual average risk of $500,000. Oh, I forgot to tell you one thing, which you will not see if you look at the average, that in town B, once every 100 years, all 100 houses burn down. And the risk is the same.
Right.
To quote Lewis Black again, are you shitting me again? Do not blame the fire scientists.
Mm-hmm.
They are getting this right. What's happening is when they communicate it to the outside world, some bozo says, give me a number. Right. A number is not going to do it. So the nonprofit, our goal is to make uncertainty actionable, whatever the heck that means. Well, it means we've created open standards for conveying uncertainty as auditable data, whatever the heck that means. Okay, let me put it to you another way. Aon creates a complex wildfire simulation. It might take days to run. Now, there's a city somewhere that our friend Shane at GFOA is working with who says, how is wildfire risk going to impact my finances? In particular, a city has something called reserves or a rainy day fund. Mm-hmm. How much do I have to put in the rainy day fund to deal with wildfire risk? What happens here? Oh, something popped out of this. This thing, by the way, had like thousands and thousands of simulated runs, right? This thing comes out. It encapsulates thousands of possible die rolls, and it goes into a simulation that I'm going to show you here in a second. I'm going to show you what I mean by making uncertainty actionable. There was this ginormous fire simulation running on a ginormous supercomputer that I couldn't understand in 1,000 years. And it spat out thousands of trials. And what we have here is a 10-year period. And what we're looking at is the chance of our reserves going dry due to wildfire. Oh boy, in year 10, it's 13%. By the way, this is a native Excel model. It does not have any add-ins or any macros or anything like that. It's just a pure Excel model. That we've got 20 million in reserves, right? Mm-hmm. Remember, we're sitting around. This is city council, whoever they are, right? Oh, what do we do? What do we do? Okay, well, what if we put in 30 million in reserves? Then what would happen? Click. It went to 10,000. It went to a 10% chance of exhausting our reserves. Here, Control Z. But it's 10,000 trials because it's 1,000 trials per year times 10 years. So look, Control Z, I'm back to 13%. Control Y, I'm down to 10%. Right. See, you didn't think you could unsimulate. No, look, Control Z, minus 10,000 trials. Control Y, plus 10,000. Okay, so we could put 10 million in reserves and get down to a 10%. Okay, here's something else we could try. Let's go back to 20 million in reserves and our 13%. Oh, but what if we bought insurance? Oh, now we're down to 6%. Oh my goodness. How is the city council discussing this now? So I want to describe what coherence buys us here. Let us take a climate change model. I'm talking strictly about sea level in this case. We create SIPs of sea level from this model. What is a SIP? It stands for Stochastic Information Packet. It's 10,000 die rolls. Mm-hmm. And guess what? It's only one thing. It's sea level rise. So what do we mean by the word coherent? Well, you will notice that at every little spot, we don't know what the sea level will be. Yeah, but it's the same everywhere. That's why they call it sea level, right? So you're not going to have sea level going up 3 feet in the Pacific and down 3 feet in the Atlantic. Sea level is what it is. And notice This might comprise 10,000 numbers stored in the cloud. Then we put in local knowledge. And the local knowledge now has to do with your tide basin, your buildings, but we put it in what? Well, Excel or Python, or do it with pencil and paper if you have to, or an abacus. See, the uncertainty is embedded in the data. It's cross-platform data. We don't care what you're using. We have disaggregated a ginormous model that is collapsing under its own weight. Think of it as a sandcastle. We've broken it into Lego blocks. And so each of these simulations produces its own sip of economic impact.
Right.
Oh, and here's the star of the show, the summation sign.
I jokingly said to you earlier today that Warren Buffett, running a big insurance company conglomerate, Berkshire Hathaway has various insurance companies under it. They should be all over. They should be all over this.
Stay tuned for part 2 of this episode of The Valley Current.